webinar that we're going to cover a new product called the OrCAD Sigrity ERC. I'm Jerry Long, a Senior Applications Engineer for EMA. I'll be going through a series of slides kind of introducing the topic, and then I'll bring up the tool and show you more or less what it's intended to do in terms of cross-linking and everything, cross-probing with the PCB editor, the layout tool, and basically just allow you a good basic level signal integrity flow. So we'll go ahead and get started here. All right, well, this product's based on the Cadence Sigrity technology, and this is the industry-leading signal integrity and power integrity solution today. It's basically known for what's known as power-aware signal integrity. So it's usually the product of choice for just about everyone doing signal integrity analysis today. You have the options of even including a 3D field solver if necessary for things like three-dimensional via analysis and things like that, difficult return paths. That's usually where 3D comes in, but in most cases you don't really need that. But however, sometimes that is an issue, and so 3D field solver is fully available to you. It is layout-based frequency domain SI and PI simulation as well. So in addition to time domain, you have frequency domain simulation. And the frequency domain tool actually gives you some very accurate modeling of your PCB structures. So you can extract S parameter models right out of your board product. It does single-ended mixed mode results and post-processing, and basically gives you a nice targeted workflow to streamline your signal integrity operations and analysis. So today we're going to be focusing on what's called level 1 and level 2. There's actually 4 levels of SI analysis. Level 1 and level 2 are considered what's I guess more or less known as basic SI. Just so it's essentially analysis of single line and differential pair simulation, as well as coupling for traces and vias in a simulation. So it's basically looking at 3 things: crosstalk effect, impedance, reference plane analysis. Focusing on level 1 and level 2 in this particular flow kind of makes everything more at a basic level here. That level 1, level 2 basically consists of these 2 flows. One's called electrical rules check, the other is called simulation rules check. And so we're going to focus mostly on the ERC portion, which is everything on the left side of this particular screen. But just to introduce it, ERC levels are geometry-based flows. It basically looks at traces and their proximities to their planes, to their neighboring traces, and gives you the results in 3 essential criteria. One, coupling coefficient, the other, impedance, and the trace reference. So these 3 analyses we'll look at in terms of a geometry-based approach and give you a very quick analysis at that particular level. You can also take it one step further in level 1 and level 2 with a time domain simulation, which is basically the same setup as what you would do with ERC. Here, it just takes it to the next step where you can actually create a waveform that runs down that particular trace and waveform analysis results. This is a very simple setup. Again, there's no models required. You just essentially define the signal itself and begin a time domain simulation that gives you basically the performance metrics very quickly. So if we take a look at this, like I said, we're going to focus on ERC, but typically when designers hear signal integrity issues, they more or less think of a very complex flow, which, more or less they think that you have an IBIS model that you need with, extraction of the PCB modeling, and you put all that together and you run time domain, frequency domain analysis. A lot of complex background is felt to be necessary for this particular type of flow. But what we're going to do is we're going to isolate that down to just the basic SI needs. So in doing that, it focuses on, like I said, more or less 3 things. Impedance mismatching, which is where most of your reflections and ringing comes from on your signals. And then crosstalk analysis. So it looks at the coupling between adjacent signal lines. And finally, return path discontinuity. So you have layer transitions or split plane situations that present difficult return paths, and so it takes a look at that and lets you know where those possible issues are. So those are the 3 things that will focus on just basic SI analysis. So when you keep it that simple, you don't really need to have a superior signal integrity background. In most designs, you take a look at designs. Ideally, those designs should be driven 100% by simulation. In reality, though, that's not practical, so you really want to focus on certain signals or certain areas of the board that you may think need a closer look, and so it's just a small subset of the overall design. And typically, PCB design rule checks are used in that fashion to determine whether there's any kind of layout issues. But DRCs typically just focus on one-dimensional things such as length, width, distance, spacing, things like that. So it's very limited in what you can do with DRCs. So what the DRCs forget to tell you? Well, that's where this particular flow is going to focus on. Let's take a look at a particular couple of cases here. We have a 5 mil trace running across a dielectric. Case 1, that dielectric is only 3 mils thick. Case 2, the dielectric is 6 mils thick. If we look at these two cases, does design rule checks look at these two things and see these as the same structures? With DRCs, it does. It looks at these and sees that these are indeed, as far as it can tell, the same structures. But do they have the same electrical properties? And in this case, no, they do not, because of the thicker dielectric in case 2. So the bottom line is that have the same, each of these structures have the same impedance, and obviously the answer is no, they do not. So let's take a look at how this breaks out and why DRC can't see this type of thing. So typically DRCs run in a pre-layout guideline type of situation where, for instance, let's just take a singular trace that's 5 mils wide. DRC dictates it will remain 5 mils wide of a certain length. As we take that trace across a couple of power planes, for instance, maybe we have a 12 volt and a minus 12 volt that it goes across. There's a void in between. Let's say that trace also goes from the top layer down to the bottom layer through a via. And then it also continues, maybe there's a couple of split plane, coplanar issues on that particular bottom layer that it goes between as well. So each one of these particular situations, across the power planes, the transition down to the bottom of the board, and then the coplanar reference issues cause certain situations that DRC doesn't really see very well. So in terms of DRC, everything's still fine here. But here we have a reference change split from that cross plane. So this will create a reference or impedance, a reference return path issue as well as an impedance issue. The layer transition can see that as well. It sees a bit of an impedance issue and a return path issue. As you're going through the via, you have somewhat of a difficult return path. You have a reference on one side that is different from the bottom layer. And then the areas for coplanar referencing, that's a problem as well. So if we take a look at what these problems might be, we can see as it goes across these voids, it presents an impedance mismatch. And in each one of the planes, each different plane that it transverses across will offer these impedance mismatches. And these voids, once you get that impedance mismatch, these voids are then good sources of radiation here for EMI noise and affects things like that. So these are the particular issues that DRC does not necessarily see well, and those are the potential problems that it can cause. One of the rules that's typically followed in DRC is that if you route traces with the 3W rule, which is if the trace is 3 times the width, the two traces are apart by 3 times the width, then you're typically safe in this area. If we take a look at this scenario, we can find out what's going on here as well. So with DRCs following this rule, with a like a 3.5 mil dielectric, a very normal dielectric thickness, you typically have a fairly tight coupling between your reference plane and your signal, so your E field that's generated tends to stay pretty tight around that particular trace. So in this particular case, where you have a thin dielectric more or less, you have a relatively good idea of being fairly safe run. Your crosstalk is probably at a very minimal level just because of the E field is tightly coupled to the specific trace, and the 3W distance keeps you in that particular safe mode, that safe zone. But if we have a situation where the dielectric grows, let's say the dielectric is much thicker now in this particular layout, you have 2 traces still 3 widths apart. Now since the dielectric is thicker, your E field begins to spread. And so in this particular case, the second trace, the victim trace more or less, now is more immersed in the E field from the aggressor. And so now you could see much higher potential for crosstalk issues in this situation. But still, DRC sees this as a valid check. So it sees that it's a 5 mil wide trace. It's three widths apart from the other trace. So it looks like it's still valid to a DRC check. But here you have a much higher potential for crosstalk. So you don't really know whether that crosstalk is high enough to really invalidate the board design or basically cause problems. So there's a particular DRC situation that's a common rule set that DRC can actually improve upon. So to summarize, The difference, DRCs are basically minimum physical requirements of design constraints, so it typically looks at length, width, and things like that. It does not look at signal proximities to the reference plane, proximities to adjacent traces, so it typically doesn't look at those types of things as well. So as a rule, it doesn't always mean that a good past DRC check means that it's a quality design. It's something that you just don't have all the information you need. So how can we address these signal quality issues at the PCB designer level in layout? Questions, when you're trying to do that at this level, most of the questions come up that is it difficult to set up, easy to use, you have to be an SI expert, tool costs, all those things are common questions, common misnomers about this type of technology. So with the introduction of OrCAD Sigrity ERC, we address pretty much all of those particular issues. Number one, one thing to note, ERCs are always better than DRCs for signal quality validation because they go beyond the minimum geometry-based checks that DRCs are based on. The tool is very easy to use. You have a minimal setup. You just identify the nets of interest, and the tool will go out and the analysis. And you can do this at the layout level, or with a PC designer layout team. And not necessarily, they could do this independent of having to rely on input from the designers themselves. So it's something that can be addressed at this particular level with, more or less an independent flow. The OrCAD Sigrity ERC, it's basically these things to remember. There's no complex modeling or setup required. The checks include the three basic checks that I mentioned that we're looking at for basic SI, and that's impedance checks, coupling checks, and then return path, reference plane checks. So let's go ahead and take a look at what this particular tool can do for us. So I'm going to open up PCB Editor. And what I have here is basically a registered DIMM circuit or registered DIMM board. This is a low-power DDR3 design. And so in my layout here, maybe I've done a bit of routing. This particular board, I believe, is complete, but in the sense that it doesn't necessarily have to be in terms of the signals that I'm looking at. But here I'm looking at my particular design, and I want to go and run some ERC checks. So in this case, what I do is I come up from within the environment, from the Analyze menu, launch the tool. So launch ERC SRC tool set here. And here I could set up some nets there, but what I'm going to do right now is just go ahead and let it just come up empty, and I'll show you how quick it is to set this thing up. Let's go ahead and let it get started. So once I bring the tool up, you'll see it brings in the particular board, so it takes that board file, brings it right into our environment, and that's typically the setup when you launch it out of PCB Editor like this. And this is, again, this is the Sigrity environment, so if you've seen that environment before, you're probably familiar with it. You see a workflow over here. In this case, it's just the ERC tool, so you see an ERC workflow and an SRC workflow, so it's just restricted to those two things. But the workflows themselves basically make this a very easy setup, very understandable flow to begin to analyze your board at this level. First step, obviously, is loading the layout file, which we just did automatically. If we want to, we can go in and check our stack up. It comes directly with the stack up information right out of the board file. So we can check our layers, check our materials, any conductivity. If we want to make, what-if analysis or change some dielectric thicknesses or something along the way, we could do that as well, just to see how it affects our design. We could prepare nets at this stage. There's two ways to do that. All we're doing next after we bring the file in is just telling the tool what we want it to go do. What are the nets that we want it to look at? So we could do individual nets from this point. The fastest way and really the most useful way is to come in and use net groups. So in this particular design, it's a DDR3 design. So what we really are interested in is really the data paths. So with each particular controller to memory chip, we want to look at the data lanes for each one of those. So to do that, we'll just set those up as what we call net groups. So here what I'll do is I'll go ahead and just set up the net group. So basically you just select that to launch the wizard. The wizard will take a look at the componentry on the board and identify each one of the types of components. In this case, I've got basically 5 different components. It's asking me for what the transmitter is going to be of these components, and in this case, it's my controller, U100. So I identify that. Next, it's asking for all the receivers that U100 is controlling. I'm not going to look at the resistor pack configuration right now. I'm just going to look at the actual memory devices themselves. So I'm going to go ahead and tell all of these components are my memory devices. These all will function as receive components. So I select that. The next step is it just wants to make sure that you've identified your power and ground nets as either a classified power net or a classified ground net. This usually aids in further design, recognition, and analysis. And then so the next step, now that I've identified the components that I want to look at signal connectivity through and make that analysis, it wants to know which specific signals between those components I'm interested in. So here I'm just interested in the data, so what I'm going to do is unselect everything, sort by net name, and just find my data line. And here's my data lines here from MDQS8 all the way down to MCB0. Those are my data lines I'm interested in, and it's really just all the data, the individual data lines, or data lanes rather, and their associated strobe. So I select those, select next. It automatically creates the net groups for me here. So this is just the analogy. I can just review what it actually created. And when I click Finish, it's going to show those net group names down in the bottom panel. And then I can come over here and just collapse all the net groups and see that it created 9 net groups. So this is typically a 8-byte lane per device in addition to the CBO lane. So I've got 9 net groups defined. So now all my basic signals that I want for analysis have been identified, so the tool sees those are the nets I'm interested in and will only focus on those areas. So the next step is to set my trace check parameters, and this basically is telling the tool I want it to go out and do impedance, impedance referencing, coupling coefficients. I want it to look at those. The coupling right now is restricted to anything over 2%. And with a rise time of 100 picoseconds, so anything that's faster than that or less coupled, it will ignore, which kind of gives me a little bit of a data control, the size of my database, essentially. And then I mentioned earlier, you can, if you went to individual nets, you can also come in and select one of these, check all signal nets, or just the enabled nets I was interested in. We're doing nets by net group here, since I identified my data lanes I want to do. I'm just going to do the net group simulation, take a look at that. I'm going to ignore the coplanar traces for this for the time being, but you could certainly come in and look at coplanar trace analysis as well. So at this point, I'm going to select Next. My parameters are set. It's just giving me a review that these are the signals that it's going to take into account. Once I click Finish, then I'm essentially ready to start. So I can go over and click Simulation. But rather than waste 2 or 3 minutes of kind of dead time while it's actually simulating in this webinar, I'm just going to load up my previous results of what I've done before. So up to now, what I've done is I've launched the tool from PCB Editor. I've identified the particular nets I'm interested in for analysis, and the tool is ready to go off and simulate. So very easy setup, very easy methodology to get started here. So I'll go ahead and load my results. I've got everything over here in this binary file already. This is a previous run that I've done with the same particular setup. So we'll let it come in. And typically when I launch a simulation, you'll see basically the cross-probing effect between PCB Editor and the ERC tool here. When you run the simulation, it's going to come up and make this cross-probing connectivity. And then you begin to see your results and everything. And it'll do the same thing if you load previous results as well. So in this case, it brought everything together. So here's where I was after my simulation ran. Now I'm just looking at results and report in my workflow. So anything that's related to just individual nets, I can see basically the tables that it presents for me. There's an impedance summary table, coupling table, referencing tables, and then I can look at layout overlays. But since I focused on data lanes, it's much more convenient to come down and look at the results when you set up net groups. You can look at impedance between these components in terms of the net groups that you've established. You can see an impedance plot, impedance table as well, coupling the same. So let's start looking at some of this information. We may want to, after we run, just kind of look at an overall impedance summary table. So if I select that, it'll bring that up. And here I can come over and take a look at the table if I just bring this little wide screen so you can see it. Here we can take a look at the results. Maybe I want to come in and take a look at, you can sort on any one of these columns, so I can take a look at which ones may have had the most, the maximum impedance values of any of those data line runs. We see some fairly high impedance spikes, but they're fairly low in terms of how much of a percentage of the overall trace length it is. So maybe we don't want to look at those right away. We come down and look at some more, something with high impedance that has a fairly significant trace run here. Let's take it in MDQ36. So our 36 our 36-bit data line here has roughly a 4% impedance length at about 92.2. So maybe that's something we want to go look at. From the data table, we could do it this way. But also take a look at that same data lane from an impedance plot. And this is where the power of this particular tool really comes into play. So you can select the impedance plot here, and this was data bit 36. So what I'm going to do is go find that in my I believe it's the next one here. So there's data bit 36. These are the various net groups that I set up, so you can see all of the 9 net groups that I'm choosing from. So I choose the particular net group that contains bit 36. What I could do is basically disable all these nets and enable just bit 36. That's the one I'm interested in. And you can see with this plot, what this plot does is it looks at the segment length, which is down in the x-axis. That's the segment length here based on, and on the y-axis, it's also, it basically looks at the impedance. So you can look at an impedance per distance. And right away, you see this particular trace had a fairly high impedance. It was roughly around 93 ohms or so for a moderately significant distance at this particular trace. So you can look at each one of the individual nets in this fashion. If you turn them on, it looks like MD or looks like bit 36 out of this particular net group, along with 38, also had some issues. Here, that's a quick way to identify that. If we want to see where this is on the board, just essentially hover over it and double-click, and it immediately jumps to that particular location on the board. And if I bring this over, you'll see that the particular cross-probing effect also brings PCB editor to the same viewing level. So right now, I have this set up to where this magenta color is what it's going to highlight for the trace in question that I basically selected on. So that's going to jump me directly to that particular point on the board. And I can begin to start taking a look at why this particular segment run here has such a high impedance value. So one way to do that is I can turn off all layers. This particular signal is on the top layer, and so I can take a look at maybe I have some look at the ground visibility or something here for the either the adjoining lower power ground plane. The top has 2 signal layers below it, and then a power ground lane. So that power ground actually has a voided area around that segment. So there's probably a pretty good indication of what's going on there. You can see that exact same trace over here. This is the area it's looking at. This is MD36 on that. So if I saw something that I can address with this void in some way to solve this or some way to improve that particular impedance run, I can come right over to PCB editor and begin to edit that and make that particular change, and then basically restart the database there and run the ERC again and see how that effect was able to be improved upon. That's kind of the impedance flow. You can look at the other signals in the impedance plots. You can come down and select different, each one of the net groups that you assigned gives you this particular impedance plot that you can directly go. And then the layout overview is very, very handy for that. The last thing is maybe some upper and lower reference tables. We can take a look at that. We'll bring that out. We can see here, this will give you a breakdown of the reference discontinuities, the number of reference segments that'll go through there, and you can sort on the particular data lines as well. On those, they'll give you that particular information. Basically do the same thing. Go through your coupling analysis and impedance analysis. From your layout view, essentially just dive right in. You can see how these are connected here. You dive right into those signal areas. Finally, as the last step, you may want to generate the HTML report out of this tool. This is a very powerful report that's generated. I've already got it generated down for this particular run. So if I come through here and just open this up, it's an HTML-based report. So I can come in here. The first thing it does in the report is tell me the general setup that I had, the board stack up, the various coupling, impedance, and reference check options that were selected. the net groups that were defined, it goes through that. And then it begins to tell me all of the particular summary results. So here's the overall board routing information, impedance summary table. Here, this is an HTML-based file, so you can come in and actually do sorts on it as well. If you need to come in and find certain areas out of the report, you can certainly do that as well, sorting on certain areas like maximum impedance, for instance. Down at the bottom is the coupling table. So it does the same thing for that. And then the top, it gives you the top 5 regressors for all of your crosstalk signals. So for instance, take a look at MCB0. Its top regressor is 1. The next one is 4. The next one is in MDQ22. So you can continue to look at those results. And then down here at the bottom, you can look at each individual net group, where it is located on the board, any of the issues associated with impedance plots or the coupling plots with each one of those. Basically a nice consolidated report for sign-off, essentially. You can use this for all your documentation for sign-off for your particular layout needs. And we'll come back to our presentation here. So in summary, the idea is that ERCs are much better than DRCs just because of the fact that they go beyond what DRCs look at. DRCs, like I said before, are just things that are just kind of constraint-driven, lengths, widths of traces. ERC looks at proximities of adjacent signals, looks at proximities of reference planes, and gives you a good geometry-based rule checking system that's easy to set up, easy to use. It gives you nice cross-probing into the PCB editor tool, so you can go back and forth, make edits on the fly, rerun the analysis and see how well the that particular edit change affected your results. And finally, it gives you the ability to identify and quickly address those signal quality issues right there as you're going through the layout process.